You know the answer to this without even rolling it. Faith. It's 1 in 6, isn't it?
1 in 6.
It's 1 in 6. Theoretically speaking, you should be a 1 in 6 chance, which ends up rounding to 0.167 to 3 decimals. 0.1666666 repeating, but 1.167 to 3 decimals. And that'll be the same all the way down. Is that fair? Notice the similarity between the empirical and the theoretical. Even if we slap a margin of error on those, it's going to be very hard to tell them apart. In our particular experiment, we had more 5s than 1s, and we had the fewest number of 3s. Assuming I counted right, which is not, I wouldn't assume that. But assuming I counted right. But that's just a random fluctuation in the system. I've had years where there are more 6s than 1s, and years where there are more 1s than 6s. And sometimes there are 2s and 3s a lot, and then sometimes we have a slight number of 6s. It fluctuates. It's not going to be perfect. Perfect is for the theoretical probabilities. Empiricals are going to be close to perfect if they're done randomly enough, right? The reason I put extraordinarily limited, and whoever asked me why is perfect in quotes, the reason for that is if Gallup wants to go out and get the percentage of people that are in favor of keeping the nurse quarantined in New Jersey, they have to give you an empirical probability, don't they? Because what's the only way they could give you the theoretical probability of the percentage of those in favor of keeping her quarantined? You'd have to ask every single person in America to get that theoretical probability, right? And you see how that's impossible? Because it's not like rolling a die. People could say, oh, it's 50-50. You either do or you don't. Well, that's like saying every time you cross the road on College Way, there's a half a chance you're going to get hit. Because you either do or you don't. But you're assuming that they're equally weighted. That's not true, correct? Well, maybe, Kelly. But you can't assume that they're equal, correct? You can't assume just because there are 2 outcomes, they're equally weighted 2 outcomes. Is that fair? Thank you for that. Thank you for that. Now, I want to now bring home one last point that's very, very important. Did you notice what this all added up to?
101%.
You guys did notice. You guys did notice. If you add up this entire column, let me slide back to the camera so I can see this. If you add up this whole column, it sums up to 1.000. Maybe off by 1,000th or a 10,000th because of rounding, but pretty damn close to 100%. How about this right here? Same. 1/6, 6 times is 100%, or 1. That is one thing I want you to kind of hammer in right now. That's part A, B, C. Yes. C. Watch this. See if you buy this. The average of that P of X column.
Is that the sum?
The sum, sorry, writing sum. The sum of the P of X column is 1 or 100%. I don't care how you write it. 100% or 1 as a decimal, they both mean the same thing. That will always be the case. And it has to be the case because the random variables that you've indicated in the left column are everything that possibly could happen. So that means 100% of the time, one of those things is going to happen. If it doesn't happen here, it's going to happen here. If it doesn't happen here, it's going to happen here. If it doesn't happen here, it's going to happen here. If it doesn't happen here, it's going to happen here. If it doesn't happen here, it has to happen there. Is that fair? Is that good? Uh-oh. Everybody okay?
Yeah.
Okay. Now, Scott, go.
I was just curious, because like, you said you miscounted.
I did.
Off of this, couldn't we figure out which one was probably most likely the one that you miscounted?
You would go with which one, on average?
I would choose 2 out of them. So there would either be 3 or 5.
Because they're the most extreme, right?
Well, they have only 2, like